Okay, so again, we're going to start with just a warm-up, and this is kind of to show you that what we're doing today is actually something we have already covered in this course. We're now just giving it a name, and we're looking at it in terms of a distribution. So the warm-up says a bag contains 8 green marbles, 3 white marbles, and 5 red marbles. You reach in and pull out 5 marbles. What is the probability that you select 3 green marbles? So again, you've seen this question lots. This isn't new. So what I want you to do right now is pause and just try and answer this question as best you can. Okay, so hopefully you have worked that out and you're back to us. Let's just take a look at the solution. Hopefully you came up with something similar to this. So the probability of getting 3 green is going to be the number of ways I can select those 3 greens. And I also have to select 2 other colors, so 2 not green marbles. And that's the number of ways of getting what I want. It's the number of different outcomes that match my particular event of 3 green marbles, over top of the number of ways of just having any outcome whatsoever. So just selecting any 5 marbles. Okay. I'm going to color code this a little bit just to connect it to the next line. So for the number of 3 green marbles, number of outcomes that have that would equal 8 choose 3. The number of outcomes that have 2 green marbles, or sorry, 2 not green marbles, again, just looking at the not green marbles would be 7 choose 2. And the number of total outcomes for just picking any 5 marbles will be 15 choose 5. Again, on the top, the biggest mistake that people make in these types of distributions is they just put the 8 choose 3 and they forget about the 7 choose 2. If you just include the 8 choose 3, that's just looking at how many ways you can pick the green marbles. But there's more ways to actually select groups of 5 with 3 green marbles. Because you could imagine you could select 3 green and then 1 red and 1 white. Or you could select 3 green and then 2 whites, right? There's lots of different ways that can occur, lots of different outcomes. So keep that in mind. Okay, so you just kind of plug that in your calculator and you get this. Big thing that I also want to notice that's different here than what we did in the last lesson is that we have made an assumption here without necessarily consciously thinking about it, but we assumed we're not replacing the marbles. Okay, so this means that each individual marble selected actually has a dependent probability on the other marbles selected. Even if we're selecting them all at the exact same time, it's actually the exact same calculation as if you were kind of drawing them one at a time. So that is no longer an independent trial. Each trial now is considered one marble that you select, whether it's all at the same time or in a row, okay? So this particular type of probability distribution is called hypergeometric probability distribution. So the properties of hypergeometric probability distribution, again, they're a series of non-identical trials, which makes them dependent trials. There's always a known number of trials, which we can call R. And each of those trials is basically selecting a known number of objects, which we can call N. There are always 2 outcomes for each trial, each with a known number of objects. So either A or what's left, so N minus A. The random variable X is the number of outcomes of one type. Now you'll notice that I defined a whole bunch of letters there. I myself am not very good at remembering what letters represent what. And I actually don't show these letters R and A and stuff like that when I write my solutions to these problems. So if you're one of those people that like algorithms and formulas and you like to memorize what each thing is, I'm going to show you that as well. But I'm also just going to kind of show you how we've been doing it all the way along, which is more of a conceptual understanding. Okay, so the formula looks like this. Again, we just did it in the warm-up. It's the number of ways of selecting the one type that you've got, and you have to select the other type or the ones that just aren't that first type. Textbook calls these successes and failures. Over top of just the number of ways that you can make your selections from any of the ones that you've got. So that's the conceptual way of kind of thinking about this formula. Using all the different letters looks like this. Again, a whole lot of letters that I half the time don't remember what they represent. A choose X is the number of total of that one type, again, which some people refer to as success, number of total successful objects, picking X of those success. So in the last one, it was number of total green marbles in the bag, picking how many green marbles you wanted, which in that case I think was 3. Next one is looking at the other selections that you're making. So how many are left in the bag total that are not what you're looking at? So example, not green. So that's why it's n minus a. It's just taking away all the ones that you consider a success. Choose however many, again, remaining trials or selections there are. Over top of just how many ways can you select everything. Okay, so again, everything in yellow there is considered the success. It's the one type of thing you're looking at, and it's just number of ways you can choose, however many you want. Number in pink is just whatever is not a success. Again, some people call that a failure. So looking at the other type of outcome. All right, so let's look at another example. Create a probability distribution for the number of females selected when selecting 6 people from a club of 12 people. And there are 8 females and 4 males on this particular club. So first, again, let's just draw out all the key information. Total number of people is 12. Total number of females, 8. Total number of male is 4. Again, when it's a hypergeometric distribution, you'll be given all these totals. Whereas with binomial distribution, we were given more probabilities. Okay? The number selected is 6. And the random variable x is the number of females selected. Again, we're going to assume that once we select a female, we're not putting that female, or a male for that case, once we select a person, we're not putting that person back in the club and then possibly reselecting them, right? Imagine like you're just selecting 6 people all at once. All right, so if we want to do a probability distribution, we actually need to look at all the possible values that x could be. But first, let's just take a look at one value for x. So I'm just going to pick x equals 3. It doesn't really matter which one we do as an example. Let's do x equals 3. Okay, so let's first kind of think about what the formula is. Again, same thing we've done in the probability unit. So we have to look at number of ways we can select those 3 female. But in addition to selecting 3 female, since we're selecting 6 total people, we also have to select 3 males. And that's going to be over top of just the total number of ways I can select 6 people. Again, we're going to color code this just so we can connect it. So I'm highlighting everything that is about the females in yellow. Okay, so we've got total females 8. We've got x is the number of females selected, where in this case x equals 3. For the males, we're going to highlight that, everything in pink. So the total number of males was 4. And that's the only thing we actually had to highlight. But yet we actually have more information. Even though there's only one thing listed there that's 4, we know how many people are selected total. We know how many females are selected. So we can use a subtraction to figure out how many males we had to select, which was, we already wrote down, was 3. Okay, over top of the just total number of ways to select 6 people. So again, there's 12 people total, and we're selecting 6. Okay, so now we're just going to lay out our colors, and then we will sub in the chooses as we go. So for the yellow, that was the number of ways to select 3 females. So again, in total there were 8 female, and we were picking 3 of them, so we choose 3. For the pink, for the males, in total there are 4 males, and we needed to select 3 of them, so 4 choose 3. On the bottom, we're selecting 6 total people from a total of 12. So 12 choose 6. Then we again just plug that into our calculator. We get 8 over 33. So there's a 24% probability that you select exactly 3 females. Now, this is not a probability distribution though. This is only one particular value for a random variable. Probability distribution lists all the possible things. So I could continue to do this by hand. And I could calculate probability that x equals 0, probability that x equals 1, probability that x equals 2. But again, we have tools available to us, so we are going to the spreadsheets. Okay, so you can see here in the spreadsheets, I have laid out all of the possible options that we've got and all the key information. So I've laid out the 2 totals. The total number of people was 12. Total number of people I'm selecting was 6. I've also laid out the number of females and males we have on the original club. So number of males was 8, number of females was 8, number of males was 4. Okay, my random variable, I've made a column for that. In this case is the number of females I'm selecting. So 0 to 6, because my total number of people selecting was 6. So the most females I can select is 6. And then I have a column for probability, which we're going to put in a function. I have a column for my weighted probability in order to calculate my expected value, and we'll look a little bit more at that afterwards. So inside here, again, I'm going to use Sheet's built-in combinatorics function. So I'm going to go combin, and then I'm going to select, this is for the females right now. So there are 8 total females, That's always going to be selected from that cell. So I'm going to lock that in. Again, I'm going to put it in front of the 2. I can put it in front of the B too, so it doesn't shift sideways, but I'm only filling this column down, so it doesn't really matter. And I am selecting 0 females. Okay, that one I do want to shift down when I fill, so I'm going to not absolute reference that. I also have to select my males though. So combin, total number of males is 4. And then for the number that I'm selecting, that's going to be however many are left over. So there are 6 people total that I'm selecting, and I've selected 0 females. So what I just did there was I did total number of people selected, subtract the number of females I've selected. Okay, now let's think about the different things that we need to actually lock in. So this one here, the D2, that's where I had the total number of males. I want that to stay. So that's going to be locked in at row 2 as well. In this section, D1, that was the total number of people selected. I want that to be locked in. So I'm going to put a $sign in front of that. A4, that was the number of females I was selecting for this particular example. That's actually going to get dragged down. Okay? So I'm going to just close that bracket again. So I have a double bracket, and now I have an error popping up. So let's read this error. It says function can bin parameter 2. So parameter 2 is the second piece in the bracket. It said the value is 6. So notice the little uppy arrow here. It's referring to kind of this second combinatorics. So it says this subtraction value is 6. But it says it should be less than or equal to parameter 1, which was 4. Okay, so basically what this is saying is this is 6 and this is 4. So I'm currently asking Sheets to calculate 4 choose 6. 4 total males. How many ways can I pick 6 of them? That doesn't actually make sense, does it? I can't pick 6 males if there's only 4 to pick from. So that means this particular option of 0 females actually can't occur. So it gives me an error. So I'm going to delete this particular row. Let's think if I need to delete any other rows while we're at it though, right? The most males that I could select would be, the most males I could select would be 4. If I'm selecting 4 males, 6 total people, I'm selecting 2 females. So I can get rid of both of these rows. So I can just say delete rows. Okay. All right, so let's go back to our permutation, not a permutation, our probability. And we're going to use combinatorics to get that probability. I'm just going to type in the exact same thing I had before for the females. There are 8 total females. I want to lock that in to be that particular cell. And I am choosing, in this case, 0 females. That one I'm not going to lock in because it can drag down and change 2, 3, 4, 5, or 6, depending on which case I'm looking at. Okay, times the number of males. So number of males in total is 4. Again, I'm going to lock that in so that it's always 4, or always whatever is in that cell. And the number that I'm picking is going to be 6, which is the total number of people selected, locked into that cell, minus the number of females. It's how many people are left over. Okay. I don't want to lock in the A4 again because that 2 female was that particular example. I'm going to do a double close of my bracket there. 1 to close just the subtraction and 1 to close the combination. So that's my numerator. That's the number of outcomes that are going to get me 2 females and 4 males. I have to divide that by how many ways can I just pick 6 people. Okay. So just picking 6 people out of 12 will just be 12, choose 6. Okay, I want to lock both of those in. This denominator is always going to be 12, choose 6. Okay, so I do that and I press enter, and you can see we get our probability with way too many decimal places. If you ever don't want to display that many decimal places because it's just not necessary, on Sheets you can just press decrease decimal places and it'll show you less, or you can go format cells and do it that way as well, right? We only need to the nearest 100 is fine. 100th, I should say. So if I drag this down now, what you're going to notice, our sum is 1. That's great. That sum function was still left over because I just copied it from our last example from the last day. But if I click on this one, just go through that again. Okay, so this first combinatorics was selecting our females. So B2 again was the total number of females. Okay, A7 was 5. That was particular number of females we were looking at in this particular row. So that was 8, choose 5. For my next one, we're looking at the number of ways I can choose the males. So the male, D2, was the total number of males, which was 4. Choose, then I did a subtraction. Total number of people, 6, minus the 5 females. So that meant there was 1 male that we were selecting. So that combinatorics was 4, choose 1. Again, divided by the total, B1, number of total people. So 12, choose D1, number of people selected, 6. So that just kind of goes over again what that function is. Okay, so we can actually, we can graph this as well. So if we select what we want to graph, we can select the headers as well. And we just go insert chart. You can see that Sheets gets a little bit confused because that happens sometimes with Sheets. It's trying to graph both column A and B as separate things, and we don't necessarily want that to occur. So for our x-axis, that's where we want it to come from the number of females selected. So that's what we want right there for our x-axis. So now we've got our labels down there, so that's good. If we go down to our series, now you can see it's plotting number of females selected, which is our column A, and it's plotting P of X. We don't need it to be selecting number or graphing number of females selected in terms of those values. That's what those red, that's what those blue bars are. So we want to get rid of those blue bars. So now we have this, and you can go through and you can add your labels for your y-axis and your x-axis and your title as well through Customize. So be sure to do that. Okay, next what we're going to look at, I'm going to zoom back in. Actually, just looking one more time at the graph, you can see that it ends up being symmetrical in this case, which is kind of interesting. You might learn about other types of distributions if you do more probability type courses in university. Hypergeometric is what we're doing right now, but the textbook also looks at geometric, which is kind of a skewed distribution. So just kind of keep that in mind as well. Okay, so now, if we go ahead and zoom back into the actual table here, what I'm going to do is I'm going to do the weighted probability. The formula for expected value for any distribution that always works is the sum of x times p of x. So that's what we're going to try right now. Okay, p of x times x. I know that's backwards, but multiplying doesn't matter what order. Okay, and then I'm going to drag this down. And I end up getting 4. Okay, so I'm just I don't need all those decimal places. That's a little foolish. There we go. So I end up getting 4 is the mean for the number of female supporters. Okay, now let's think about if there was maybe a quicker way to do this. We already had a spreadsheet, so it wasn't that long. But if you remember in the binomial, we just looked at the number of things we were selecting. In that case, it was liberal supporters, times the probability of selecting a liberal supporter. Let's see if we can use that same idea here, right? Okay, so the number of people we're selecting is 6. The number of females is 8, and the total number of people is 12. So the probability of me selecting a female, if I just select one particular person, would be 8 out of 12, right? The number of people I'm selecting is 6. So if this is the same idea as binomial, then I should be able to say, okay, just 6 times the probability of me selecting a female on one particular draw, or one selection, 8 divided by 12. That equals 4 as well. So there's a little bit of a faster way of doing it. All right, so just looking back to write down our solution for the expected number of females that would be selected without using the chart and doing the XPX method, which will work, but it just takes a little bit longer. We can use this formula now. So this is the conceptual understanding, which is how I kind of think about it. So the number of selections is everything that we dealt with in orange from the above. Probability of one selection, in this case, it's probability of that one selection being female, okay? If you want to think about it in terms of the letters that I defined before, it's R times A over N. Again, R is just the total number of selections that you're making. A is the number of female selections you can possibly get, or number of females that exist, over top of the number of total people that exist, okay? So then you end up getting 6 times 8 over 12. Again, 6 is the total number of people selected. 8 is the total number of females out of 12, the total number of people, which equals 4. Okay, so Again, expected value means if we were to repeat this many times, the mean number of females that you would select would be 4. Okay, so just kind of big summary of this lesson now. This is what we've done before. Uniform probability distribution and non-uniform probability distribution. In order to calculate the probabilities for all of those, you're just using counting techniques that we have done before. And then you're really just looking at the number of outcomes. And then we also looked at binomial probability distributions, which is what we did in the last lesson. And we developed a formula for that. And we developed a formula for the expected value for that as well. And today we added another non-uniform, which is hypergeometric. So the difference between binomial and hypergeometric is that identical trial versus non-identical trial. So in binomial, they're all independent trials. The probabilities are the exact same, and you're usually given the probabilities. In hypergeometric, you're given totals, and you're drawing and you're selecting and you're not replacing. So it's dependent probabilities, but they both have 2 specific outcomes for one particular selection. There's the formula for hypergeometric for probability, and there is the formula for hypergeometric for expected value. Okay, that's the end of the lesson.